actually see his slides.
Okay, good afternoon. My name is Jay Baker. On the yellow team, 1 of 3. The other members are Joel Wood and Jamie West. Today I'll be talking about the spray group pressure station, steady step behavior, and step modeling. Overview is a schematic of the system, the result of the steady state operating curve, the FOPDT, which is first order plus dead time theory, model theory, FOPDT result, and conclusions. The schematic is of the pressure system along with 3 boosts. We have the pressure sensor, which relays back to the computer and gives us our results. We have a MT is specified by the user, and in the middle is our system, which is an electric motor and a fan. And the output is pressure resulting from the motor's response. Do you want to cover all this? Okay. This chart, this graph is showing that pressure of the...
Each of these presentations is like you're going to the customer and the customer's people. And believe it or not, the last presentation, not everybody was there. And so somebody might be there that didn't get this. You with me?
Yep. Totally.
And plus the fact somebody might have been there and they might have been asleep, or might have, in 2 weeks they might have forgotten.
This graph shows experiment data at 85% input power. It found steady state at 49 plus or minus 0.6 centimeters of H2O. From the data that we compiled, we were able to form a steady state operating curve with 3 different input ranges, 5 to 30% input power, 35 to 55% input power, and 60 to 85% input power. We found that the slope is 0.8 centimeters of H2O per percent power. This is the step-up function from range 15 to 30 centimeters of H2O. Our delta M equal to 20, delta C equal to 15. Our T naught was 0.1 second, and tau was 1.5 seconds, and K ended up being 0.75 centimeters of H2O per percent. This is our step-down function from the range of 30 down to 15%, or 15 centimeters of H2O. We ended up with the same M of 20. The C was 14.8. T naught was 1.1 second. Tau was 2.1 seconds. And K value equal to 0.74 centimeters of H2O per percent. These are the average values of T naught per the ranges. Tau values per range, and K values per range. I'll speak more about that when I get past our modeling and experiment data, where I have it broke out in experiment and modeling. This modeling equation is CT equals A times U T minus TE minus T naught times K times 1 minus E raised to the negative of T minus TE minus T naught divided by tau. Using that formula in a range of 15 to 30 centimeters of H2O, we were able to find the following parameters: TE being 15 seconds, A being 20%, and our K value of 0.75 centimeters of H2O per percent. T naught being 4.4 seconds, tau being 1.5 seconds. used a input baseline of 45% power and an output baseline of 15 centimeters of H2O, resulting in this graph. This is from the range of 15 to 30 centimeters of H2O. We have experimental and modeling input, which fell right on top of each other perfectly. And then we also have experimental and model output, which lined up somewhat well along the curve. Our K value ended up being 0.76 plus or minus 0.02 centimeters of H2O per percent power. Tau was 1.5 plus or minus 0.3 seconds, and T naught was 1.1 second. This is our first order step down response, the time delay from 30 to down to 15 centimeters of H2O. We ended up with the same T naught, 0.1 second. K value was 0.74 plus or minus 0.15 centimeter of H2O percent power. And our tau was 2.1 plus or minus 0.2 seconds. Average T naught values per range. Experimental data is such a short range that it's hard to measure, even if we did flow or zoom down onto the graph. But we did result as a 0.1 on both experimental and model data. Average tau values per range. On experimental step up, we ended up with a 1.5, and on step down was a 2.1. We had a difference in 2 on air, on step down, and on step up we had error range of 0.15. On the modeling, it was a constant 1.5. Average K values per range. On experimental data on step up, we had 0.76 with an error range of 0.2. On step down, we had 0.74 with error range of 0.15. In conclusion, based on the experiments done, we were able to understand the steady-state operating range of the system and how it allows us to predict output pressures. Operating ranges for our entire experiment was 5 to 45 centimeters of H2O on the first order plus dead time experiments. The first order, or FOPDT transfer functions, are important to approximate the response of dynamic processes. The modeling graph and experimental graph were consistent with each other after a little bit of manipulation. And pressure system ended up being a quick response time of 0.1 seconds. The differential in tau, however, on step up was 1.5 plus or minus 0.3 seconds. And we had a little bit longer delay before steady state was reached on the step down of 2.1 plus or minus 0.2 seconds. Are there any questions?